I do enjoy speaking with him, but the one time he stuck for Dr. Fani, I turned into a complete blood of idiot. Like I was literally so stressed out when I said oxygen was not like but he was a lot of us. Yeah. Really good. Basically, you just have to be a little fast. You can get the answer going. I agree with everything.
It's scary. Like personally, I want to go into the education system because education is the root of, like, a lack of education is.
Okay, time to begin. So as I said in an email earlier today, I didn't hear any pushback on, or maybe I said it yesterday, I didn't hear any pushback on sliding the exam forward to Tuesday, so the exam will be on Tuesday during class, and I'll try to do the same kind of thing as last time where there's a time for Q&A right before the exam. Although don't save up huge conceptual issues to right before the exam. It's always good to get those cleared up ahead of time. So we want to clear up the remaining Chapter 5 homework questions, and I'm certainly willing to entertain those now. And now we're getting into the beginning of Chapter 6. We've done the stuff that's, we've talked about work and the relationship between work and kinetic energy, network and kinetic energy, from the work kinetic energy theorem. Anybody have questions they want to talk about at the beginning? I'm hoping that means everything's just crystal clear rather than everyone's too busy to really get into the homework. Chapter 5, you're welcome. Chapter 5, Part 1, I think, is due today. Chapter 5, Part 2 is due tomorrow, I think. I probably gave you a little bit too much time to work on those because we really should be into Chapter 6 doing the homework now, just because I have to tighten up the due dates before the exam that's coming up next week. Yeah?
I have a question about one of the homework.
Sure.
Do you have the paper?
I do. Of course, I've got so many things here. I've got to find the right one. Are we talking about Chapter 5 or Chapter 6?
5, Part 1.
Okay.
Number 7, specifically about
The conical pendulum one? Uh-huh.
I can't figure out how to get speed, but almost certainly. I've tried. Got the wrong answer a few times.
Well, so the way to get it is, the first thing I need to do is figure out what the tension in the string is, and that's from F net y equals MAY, which is 0, vertical, right? And then we do the horizontal one, which has the v squared over r for the acceleration. You know, if there's more desire to talk about that problem, we can. It sounds like maybe we need to look at your numbers, which we can. Yeah, but in front of the class might not be the best time to do that. If you have conceptual problems with how to approach it, but it sounds like to me that you're approaching it the right way. There are two forces. Only the tension force is going to contribute in the mv squared over r, F equals ma thing, right? But we can certainly set it up. Let's just do a quick version with my numbers that are here. Let's see. Yeah, I've got the board shown here. So we're talking about problem 7 in chapter 5, part 1. We've got a conical pendulum. So this is at an angle in mine of 34 degrees, like that. And it's going, this is of length 3.1 meters. This string length to the point where it's attached up there, and it's rotating in a horizontal circle. And so I'm going to put some axes on this. So my free body diagram, let's just put it over here to the right. We've got the tension pulling in the direction that the string is attached. If that angle is 34 degrees, then certainly this angle is 34 degrees for mine too. And then I've got an mg going down. For me, this is 5.2 kilograms. So this would be 5.2 times 9.8. That's the free body diagram, step 1. Step 2 is axes. I know the acceleration at this instant is toward the center of the circle, so I'm going to choose that to be x and y to be vertical. And so F net y equals MAY would be, maybe my t doesn't look so good there. Let's put it over there. T cosine 34 minus 5.2 times 9.8 equals 0. That allows me to solve for t. That's the y. F net y equals MAY. Then F net x equals MAX once I know t. This has 0 x component. It's moving, it's pointed only along the y direction. So I only need to include this one, and it's going to have a positive x component. Positive t times the sine of 34 degrees. That's equal to the mass of the object in the free body diagram times v squared over r. I guess one place that could, you could get fooled is put in r equals 3.1. But the radius of the circle it's traveling on is certainly not 3.1 meters. It's quite a bit smaller. 3.1 times the sine of 34 is going to be this distance there. That's from this big right triangle. We know the hypotenuse and we know that angle. So I need to figure out what my t is from the first equation, plug it in, and then solve for v with a square root. Anything else on the homework? Caitlin? Number 2 on part 2. This is the multiple choice one that's on there? Okay. Yeah, those are a little bit dangerous because you can lose credit, a lot more credit, on the regular problem where you're putting in numbers. Even if you get it correct on the last try, you still get close to 80% of the credit. It just doesn't take off that much. But when you're doing a multiple choice one, you can lose a lot more because at some point you're whittling down how many possible answers are left as you make incorrect guesses. So you definitely don't want to guess your way through those. Let's see. What's the ratio of the gravitational force on an astronaut when he is in a space satellite in a circular orbit of 385 kilometers above Earth? So one thing is that's an altitude. So here's Earth. This distance here we might call the radius of Earth. And then there's something orbiting in a circular orbit, space shuttle with an astronaut in it. And this distance is 385 kilometers. It's saying above the Earth. So 385 times 10 to the 3 meters. I'm just putting everything in SI units so I don't forget about it later on. Okay, and they give you Earth's diameter is 12760 kilometers. 12760 times 10 to the 3 meters. And the question is, what is the ratio of the gravitational force on the astronaut when he is there to when he is on the surface of Earth? So let's just write that ratio. So of course the gravitational force is given by g m1 m2 over r squared. And so I'm going to write that in a ratio. I think they said we want it in this situation. I don't know what the mass of the astronaut is, but that's one of the things that's going to cancel out. So in the numerator of my ratio, capital G times the mass of the astronaut times the mass of Earth divided by this, let's just for right now call this R, okay, over R squared, divided by, we want the ratio of that to what the gravitational force is on the surface of Earth. And the only thing that changes there is that R is then R Earth, because if the astronaut is down here, is a distance of R Earth away. Now, I could have put this in as just using mg there, but you see the advantage of putting the big mess in the denominator is that a lot of stuff is going to cancel out between numerator and denominator, right? I've got a common, if you want, you could invert and multiply. I don't know how good people are with fractions like this, but when you have a fraction in the denominator, you can put the reciprocal in the numerator, and that's the same thing. Sometimes people call that invert and multiply. So this is equivalent to GMME over R squared times the reciprocal of this, which is R Earth squared over GMME. So that's what we're trying to calculate. And now we've got a lot of common factors. I didn't really want to put in that factor of capital G. It's a big mess. I didn't know what the mass of the astronaut is. And I don't really want to put in the mass of Earth. It's a big scientific notation number there. So in this case, you know, just putting in the final numbers without calculating it, radius of the Earth squared is 12760 times 10 to the 3. I need to square that in the numerator. And in the denominator, I need 385 times 10 to the 3 plus 12760 times 10 to the 3. That thing squared. So I think that's the ratio they're asking for. More questions on that one? Did that help, Caitlin? Anything else? Chapter 5 or chapter 6? All right. Good. Well, keep on asking those. More time after class. Tomorrow during class, I'll put a call out for more homework questions. We want to make sure we keep taking care of those so we keep up with it and really start chipping away at that chapter 6. Okay, let me go to the screen share here and remind us where we left off yesterday, which was with something called the work kinetic energy theorem. We spent a lot of time talking about work and how to calculate work. What was positive work? Remember positive work? We always have to specify with the work what force we're concerned with calculating the work for, because there are lots of forces that act on an object as it's moving around. We have to be clear about what force we're concerned with and what it's acting on. What is the object for which we want to calculate the work done by that force. And when we decided that a force does positive work when it's pushing or pulling more or less along the displacement direction. It does negative work when it's pushing or pulling more or less opposite the displacement direction, and zero work when it's perpendicular to the direction of the displacement at all times. The net work was the sum of all works, or equivalently, although it feels a little bit different, the work done by the net force on the object. That's another way of saying the same thing, but it's maybe easier to think of it as just add up all the works by all the forces as the object moves from some initial position to a final position, and through work that we didn't go into in class, although I went into great detail in the video. You can relate that using F net equals ma and our kinematics work to say that the net work done on an object as it moves from an initial state to a final state is the change in kinetic energy, where the kinetic energy is 1/2 mv squared. M isn't changing, but of course v could change from the initial to final state. Maybe the thing speeds up, so a bigger v final than a v initial. So we did some practice with that. And here was, that was pretty much where we ended with a practice problem, but there were some voting questions that they're not as exciting when they appear in the videos, but they're good to think about anyways. Here's a spaceship moving at 400 meters per second towards Alpha Centauri in deep space, so there's no gravity. The only force on the spaceship is going to be its thrusters, right? It's sort of interesting, you know, if you don't think about rockets and things like that, or thrusters on spaceships, that the reason there's a force is because you're sort of throwing stuff out at really high speeds out of the thrusters. And if the ship is pushing that out hard, then that stuff is pushing back on the ship and makes it go in the opposite direction. So in this case, we've got a ship that is, it's going towards Alpha Centauri, but it's got its thrusters aimed toward it. So it's sort of aimed backwards with the nose of the ship in that way. And it starts blasting them in that direction, which slows it down. And then it comes to rest, and it starts accelerating in this direction. So it completely turns around. I mean, it doesn't turn around its orientation, but it starts moving in the opposite direction. And the question is, how much work is done by the thrust force on the ship during this period? And the answer is it's 0. Why is it 0? What was the argument there? I mean, it superficially seems like, look, the thrusters are blasting in the same direction the whole time. So shouldn't they be doing more and more and more work as time goes on? They're always pushing on the ship in the same direction, away from this galaxy. Yes? Yes, we got to think about the displacement. So the force on the ship, as the ship is moving towards Alpha Centauri, is the force from the thrusters is pushing on the ship away from Alpha Centauri. So the force on the ship is this way. The ship's still moving for the first half of the motion until it comes to rest. That's negative work. Displacement in that direction, force on the ship in this direction. So the thrust force is doing negative work. Then, after it slows to a stop and starts going backwards, it's speeding up in the opposite direction, its displacement's in that direction, and the thrust force is still in that direction, so it's doing positive work. So that is a qualitative way where you might say, well, it seems like it could be 0, right? Because there's a negative work and a positive work. How could I be sure with a slightly different argument to say that it was exactly 0? Rather than part of it's positive and part of it's negative. It seems like it would be 0, but maybe you're not so sure about that. It's from the work kinetic energy theorem, right? The initial speed is the same as the final speed, right? So when we calculate 1/2 mv squared, we don't know what the mass of the ship is, but it's not changing. There's a little bit of loss of mass because you're throwing a tiny bit of fuel as gas out of the thrusters, but that's presumably completely negligible compared to the mass of the ship. So 1/2 mv squared would be 1/2 m times 400 squared. That would be 1/2 mv final squared. And then, you know, same thing for the initial. So the difference in the kinetic energy, there's no change in the kinetic energy. It's going just as fast at the end as it was at the beginning, and therefore there's no net work done on the ship. Okay, no network. That's not what we asked for. How much work was done by the thrust force? Well, the thrust force is the only force acting on the ship, and so the net work is the work done by the thrust force in this case. It would be more complicated if there were 4 forces acting. We could learn something about the net work done, but we might not be able to learn anything about a particular work done by a force. But in this case, there's only one force, so the net work is the work done by that force. There's another question of, well, what about the first half of the period? That's negative work, right? Because the thrust is pushing it away from Alpha Centauri while it's still traveling toward Alpha Centauri. That's the hallmark of negative work. Second one, car starts from rest. This one is usually trips or people just don't have the right intuition about it, right? You think, okay, car's accelerating, going 0 to 30 or 30 to 60, which requires more work. And what's doing the work on the car? Well, if you look from the outside, what is pushing on the car? Strangely enough, the road is pushing on the car, right? You can think of, if you're in the car and your car starts trying to spin its wheels in this direction, it's trying to push the asphalt back in that direction, which means the asphalt's pushing on it forward in this direction. That's Newton's third law. So it's the asphalt, maybe friction force from the asphalt that's pushing it forward. But in any case, which takes more work? We're talking about the work by the asphalt. And it seems maybe superficially they may be the same because it's the same change in V. But the problem is this V squared in the 1/2 mv squared. It gets really big. When you square something, it starts getting big really fast as that thing that you're squaring gets a little bit bigger, whereas it doesn't increase so fast at the beginning. That's when you're on this part of the parabola, but then it starts going up really quickly. So a little example, you know, the miles per hour aren't so intuitive here, but if you say, let's compare, you know, let's say the mass is 2 kilograms. Why would I want that? Well, because I have a 1/2 in front of it. So 1/2 m is just 1 in that case, if we ignore the units, right? So I just have to do V final squared minus V initial squared to get the work done in joules. And let's compare 0 to 1 to 1 to 2 meters per second. And when you do that, you would say, well, I have to do 1 squared minus 0 squared, that's 1 joule of work required. Whereas in this case, I have to do 2 squared minus 1 squared. That's 4 minus 1 is 3 joules. So as you go faster and faster, it takes more and more work to speed up the same amount. So as you go from 0 to 100 miles an hour, it takes not that much work to go from 0 to 10, then more work from 10 to 20, more work from 20 to 30. It keeps increasing the faster you're going. Okay. And any questions on that before we finish up the worksheet that we had from last time? What is it? I've got to remind myself here. Let's see. Huh. Oh, I also forgot to email the class. Jose asked me after class about problem 3, and I realized that in the version that I gave to you, so if you'll look at problem 3, and I don't know how much you wrote about it, but in the explanation of part C, it should say the following, and I think I printed it without making this change in there, which is in the changes in my version, which I printed the solutions for. Let's see, 3C. It should say I'm sorry, 3D. No, there only are C parts. Is there a D on the next? Oh, D's on the next page. There we go. Oh, no, it does say it. Jose was asking me where the 20 meters per second came from, and it is printed in here. Maybe I'm sort of confused about this. So if you look at the next page that has the ramp, there's part D at the top. It doesn't say anything about 20 meters per second. I would be surprised that it does. Okay, yeah, so we talked about, for some reason, I thought this 20 meters per second was missing from the printed version, but now I'm seeing that it's not. How much work is done by the soil contact force is, at least in principle, hard to imagine how you would do it because the force is complicated. It's not constant. And as that thing goes down into the soil is compressing more and more and more, which means the force is getting bigger and bigger and bigger. And I don't really know anything about how big it is at any point on the way down to coming to rest. And in this case, we can calculate it by using the work kinetic energy theorem. We know its initial speed, 20 meters per second. We know its final speed, so we can calculate the change in 1/2 mv squared. And that's equal to W net. And W net is coming from the work done by gravity, which we calculated above, and the work done by the soil force. So we can kind of back out the work done by the soil force, even though we don't know anything directly about it. Did you have a question, Sam? Oh, I do. Okay, so I thought that was something I messed up with, but maybe I didn't. So in problem 4, it's a little bit confusing. Let's just talk through it, the setup of it together, and I'm gonna let you think about it. We've got a frictionless inclined plane. There's a ball on it, but the ball A ball won't start rolling if the plane is frictionless. If it's frictionless, the ball just slides down without rolling. So we don't need to worry about the rotational motion of this ball. I'm not sure why I called it a ball. I think it's because it's going to go into a pool of water. And the pool of water, I was imagining you might have some complicated motion if you had a cube-shaped kind of thing that was obviously sliding along the plane. But in any case, slides along the plane for a distance of 4 meters as measured along the plane. It's 0.2 kilograms. And then as soon as it hits the end of that ramp, it enters a pool of water, which is level with the bottom edge, and it doesn't hit the bottom of the pool, but after sinking a distance of 40 meters vertically towards the center of Earth, the ball then is slowed substantially. We didn't calculate yet what its speed was at the bottom of the plane, but you'll find the water has really, really slowed it down a lot, right? It might be going really fast after going that 4 meters, and then the water is going to slow it down really quickly. So by the time it's gone down a depth of 40 centimeters, it's only going at 35 centimeters per second. You could imagine that being true. And we're supposed to find some various works and changes in kinetic energies of the ball in different parts of motion there. So see if you can think about that. We're, of course, using the work kinetic energy theorem. So let me just back up to that statement here on the slides. You know, one of the reasons I don't want the ball to start rotating is we said we're only talking about particles when we're using the work kinetic energy theorem. And if the ball starts rotating, technically it's not behaving like a particle, so we can't apply the work kinetic energy theorem. But if there's no friction, there's no way it starts rolling. It just sort of skids down the plane because there's no force to start it spinning. When you're thinking about the work done by the water force, remember the water force is complicated. We probably can't calculate that directly, so we want to do it indirectly, using the work kinetic energy theorem by finding out something about the net work done on the ball during that process and then backing out the work done by the water on the ball. For the normal force there, I mean, it's fine to put that in, but yes, imagine this angle closes down to 0. That normal force would turn into vertical. Can you imagine that? So that means this angle is the same of that normal force relative to the vertical, because they would both, trace out. As you tilt it the other way, it tilts relative to the vertical by 42 degrees. put some of my numbers up here on the side of the board. How many need help on A? Okay, let's talk about it because I want to make sure that you can't really go too much farther unless you can get A, and it might be a little bit confusing. We want to use that formula that we introduced right at the beginning of the chapter, which is, again, we always want to be clear about what force. In A, we want what force is doing the work and what the work is being done on. So we want the work done by gravity on the ball, just to be very clear. And the formula we gave at the very beginning was, well, you could calculate that in general by Fx delta x plus Fy times delta y. And maybe you could align your axes with the direction the thing is moving, or you could just ignore it and you might have to use both terms. We'll see here. Now in this case, since I know, well, I can figure out how far it moves vertically, I chose, let me draw a little diagram over here. I chose, here's my pool of water. Here is this incline right there. This is 42. I chose down to be y and left to be x, just because all the, it was more or less going downward in y the whole way. You could do upward being plus y if you really wanted to. So if we're talking about the work done by gravity on the ball, what do I immediately know about this expression? What can I simplify in there in my coordinate system? X part is 0 because gravity's x component force is 0. So in this case, in my coordinate system, this is the gravitational force, and its x component is 0, right? The gravitational force is always straight down. So this is 0. And Fy, well, I know what Fy is. That's just the gravitational weight of the ball. That's the y component of the force. And that is 0.2 kilograms times 9.8. So that all that remains is for me to calculate what its y displacement component was as it goes from there down to here, where this is, 0.4 meters, 40 centimeters. How far does it go down in y? Well, I know it goes 0.4 meters there, right? So I just need to figure out how far it goes down in y here. That's this distance. If this distance is 4 meters here, then the question is, what's this vertical side of the right triangle? We can get that from our trig stuff, right? We go 4 times the sine of 42 gives me this vertical displacement plus this additional vertical displacement. So this would be 4 sine 42 plus 0.4. That would be how many meters it goes down in the y direction. That's both positive because I chose plus y to be down. Of course, if you chose plus y to be up, then there would be a minus sign associated with this force. and there would be a minus sign associated with the displacement, and with the minus minus would give plus, so we'd get the same answer. Okay, somebody help me start B. What principle should I use in beginning B? We want the same answer, but for the work done by the water force on the ball. Where could I begin with this? Can I do the same kind of thing, but just for the water force? In principle, yes, but in practice, no, because I don't know anything about how big that water force is. The water force presumably is huge when something's moving really fast, and then it gets smaller as it starts moving at a smaller speed. So I don't know anything about what the x and y components of the water force are. In fact, there are probably both x and y components, right? Because when it's going in at an angle, the water force is sort of pushing back. It's like a kind of friction almost. But that would have, in my coordinate system, both a non-zero x and y component. And the ball's probably turning as it's falling in the water, too. As it slows down, it starts to go more and more vertically. So that seems horrendously complicated. What's our only other option? What was that? The work kinetic energy theorem, right? Because one of the work, so I'm going to say my initial or starting point is when it's released at the top, and final is when it's 40 centimeters down in the water. One of the works that I want is part of this, and the other one we just calculated. So I'm going to say, let's just flesh that out here. The net work done, again, just to be clear, I'm going to put on the ball. You don't have to say by what, because net means by everything that's acting on it, is equal to the change in the kinetic energy of the ball. Let's expand that out. The net work done on the ball, and again, this is for from release to 40 centimeters down. You could write that down explicitly if you thought you might get confused about it, but you got to be clear about what your initial and final states are here. The net work done on the ball during that period is the work done by gravity on the ball during that period, plus the work done by the water. And of course, the water's not really doing any work until it's in the water, because it's not exerting a force on it while it's on the plane, but who cares? We'll figure it out nonetheless. From release at the top of the plane till it's 40 centimeters down, and that's equal to 1/2 times the mass of the ball times v final squared minus 1/2 times the mass of the ball times v initial squared. And we know v final and v initial. What's v initial in this case? 0, it's released from rest. And what's v final? 35 centimeters per second, or 0.35 meters per second if I want to put it in SI units. Okay. And this, by the way, is what we just answered in part A. So that's 6.03 joules. Okay, I'm going to be a little bit sketchy with my subscript here, but we can always add more detail in the subscript. By the water on the ball. That's equal to 1/2 times the mass of the ball. Was it 0.2 kilograms? I think so. times, I'm just going to factor out the 1/2 m so I don't have to write it twice. V final squared minus V initial squared. V final squared was 0.35 meters per second. That needs to be squared. So there's my 1/2 m V final squared. And here is my minus 1/2 m V initial squared. And V initial was 0, was released from rest. And that equation then allows me to solve back out kind of what the work done by the water was from release until it's 40 centimeters down. And we know the water wasn't doing any work here. Water wasn't even exerting a force on it until it got to the bottom. So all that work was done while it was falling in the water. It's negative. That's important. The water it was going really fast by the time it slipped down the plane, and the water slows it down a lot, almost to rest compared to how fast it was going at the bottom of the plane. I didn't calculate what its speed was at the bottom of the plane, but we can kind of see that because look, gravity did a lot of work between initial and final, which was 40 centimeters above the water. Sorry, below the water. The water does almost as much negative work. Now, gravity still wins out a little bit overall, so that means the net work was just slightly positive. And that means there's just slightly a gain in kinetic energy. It started at rest, and it was going at a pretty small speed compared to what it was at the bottom of the plane, presumably. So it lost almost all its kinetic energy because the water was doing that negative work. All right, the last two are just, I don't know, maybe they seem like somewhat random questions, but just to ask about the kinetic energy part of it. What's the change in the kinetic energy of the ball while moving down the plane? So here I want my initial to be release and final to be just reaching the bottom edge of the plane. So we're changing our initial and final here. What's the change in the kinetic energy? Well, one way to do it is with kinematics, but that's actually going to take more work than using the work kinetic energy theorem. How might I use the work kinetic energy theorem to answer C? What's the speed of the, is that what I said? No, the kinetic energy, change in the kinetic energy while moving, of the ball while moving just down the plane. You know, if we did kinematics, it would be a good old-fashioned kinematics problem. I'd have to first figure out what A was and then choose a kinematics equation and say, I know my delta X is 4 and I want to find a V final. And then once I found that V final, I could just change it into a 1/2 m V final squared to figure out the change in the kinetic energy. That would be using kinematics, but you'll find it's a little bit easier to avoid that and rather, or at least it seems easier to me, because that's a two-step process that would take a while, to use the work kinetic energy theorem. Okay, again, I'm keeping in my head, initial is release, final is at the bottom edge of the plane. It hasn't quite gone in the water yet. In that case, well, okay, what forces are available to be doing works on the ball as it's sliding down the plane? The water's not touching it, so the water's doing 0 work on it. But what other forces are acting on it? Gravity, and there's one more. The normal force. How much work is the normal force doing as it's sliding down the plane? 0, because it's perpendicular. The direction of that force is perpendicular to the direction it's being displaced. So, with that in mind, the net work done on the ball during that process from release till bottom of the plane is equal to the work done by gravity only on the ball. Because, you know, I could put plus the work done by the normal force, but that's 0. I don't have to add 0. It doesn't change anything. And and that must be our audio from Zoom, I guess. Okay. That's 1/2, well, I guess I would just write it this way. We want the change in the kinetic energy. That's KE ball final minus KE ball initial. Well, let's just write it as the change in the kinetic energy of the ball. Isn't that what we were asked for? This is what we're asked for, I think. What's the change in the kinetic energy of the ball? So all I need to do is figure out how much work was done by gravity. We really did that up above, right? It was just part of this. If I forget about that 0.4 there, this is how much work is done by gravity just going down the plane. We added some more on it there, but the delta y is just slightly smaller if we stop at the bottom of the plane. So this would just be 0.2 times 9.8 times 4 sine 42. It's not the most interesting thing to calculate. What are you going to do with that delta KE? But I just thought, you know, we've got to be able to calculate lots of different things. Sometimes the homework problems, they'll ask for a change in kinetic energy. So you don't want to be thrown off by that. But it sounds like if somebody's asking for a change in kinetic energy, it immediately reminds me of the work kinetic energy theorem. And in this case, that's a certain amount of positive work, 5.25 joules. You know, you can see in the process of going down that additional 40 centimeters, gravity did a little bit more positive work. So it was a bigger number there. It's slightly less positive when it's just going down the plane, but not allowing gravity to pull on it some more in the direction it's moving. Questions on A, B, or C? All right, D, what's the change in the kinetic energy of the ball while moving from the surface of the water to the depth of 40 centimeters? So this is just while it's in the water, same question. And in that case, well, I guess I have a couple of ways to do it. I could, again, look for the change, it would ask for the change in kinetic energy of the ball. So I could do that from hitting the water until 40 centimeters down in the water. And if I wanted to do it, I could calculate it directly. One way to do it, let me pull this over, is to just simply to calculate the change in kinetic energy, I could do it completely directly and say that's equal to 1/2 mv final squared. And I know what v final was, right? That's the 0.35 meters per second. So I can calculate this directly. But I also have to subtract off 1/2 mv initial squared. And here I'm thinking of initial was right when it left the plane. And I don't necessarily know what the speed it had when it left the plane was. I could calculate it. And in fact, that's the way I did it in here. How might I calculate the speed that it has when it hits the water? In other words, I know this is 0.2. This was given, that's 0.35 meters per second. This is the speed it has at the bottom of the plane. And I might calculate that using kinematics, but again, I'm claiming that's the more painful way to do it. It's going to require more work. You'd have to figure out what A was, AX, and then use one of our kinematics equations to figure out what V final was. How might I do it just with work that we've already done, this stuff over here? The answers that are right here. Well, we know the work done by gravity in going down to the bottom of the plane, from the top of the plane to the bottom of the plane. And that work done by gravity, which is 5.25 joules, is equal to the change in the kinetic energy of the ball, right? And in that case, V initial was 0. V final is what we're after to plug in here for the V initial for the next part of this problem, right? So I could do a little side calculation over here and say, oh, from the top of the plane to the bottom of the plane, the net work done by all forces on the ball is equal to the change in the kinetic energy of the ball. The net work done by all forces as it's going just down the plane, from the top of the plane to the bottom of the plane, is the work done by gravity plus the work done by the normal force, which is 0. So that's just the work done by gravity on the ball. And that we already calculated was 5.25 joules. That was part C. Okay, so the left-hand side is 5.25 joules. And the right-hand side is 1/2 times the mass of the ball times V final squared. And we're after that V final. minus 1/2 times m times v initial squared. And here, that's the release point. So that's a 0 squared over there. And that would allow me, this equation would allow me to solve for v final. It's maybe not too much easier than kinematics, but it's a little bit, it's at least a one step. Given that we've already calculated that 5.25, you could calculate what this v final is, and I get v final is equal to, well, I guess I don't even need to calculate what v final is, right? I'm making more work for myself. Look, this is 0. I'm sorry, that's not 0, never mind. But what I'm after is the kinetic energy at the bottom of the plane, and that's exactly what this is here. So this is 5.25 joules. I didn't even think about that. I solved for v and then plugged it back in. I square rooted it and then I squared it again. But if we want, you know, we're saying the change in kinetic energy of the ball from the top of the water to the bottom of the water, one of the things that comes in there is the kinetic energy of the ball right when it enters the water. And I can figure out the kinetic energy of the ball when it enters the water by just considering its motion down the plane until it hits the water. And then that would be the final kinetic energy that appears on the right-hand side, right? This is like Ke final minus Ke initial. This was going down the plane, and that was 0. So I can solve for Ke final. It was 5.25 joules. So this number is 5.25 joules. And then I just calculate this difference. This is our 0.35 meters per second. In any case, then 5.2 minus 5.238 joules. So when I calculated it, I got my V final. As I wasn't as smart when I was writing my solutions up here. I actually solved for what V final was here, and then I plugged it back in there. But I'm really undoing something and then doing it again when I do that. But I got V final was 7.25 meters per second. There might be a slight rounding there because I give a lot of decimal places in that number. 4 sig figs right here. In any case, it should be something that is slightly, well, I guess it's hard to compare those two, but in any case, I think, are there any questions? I feel like I'm not getting a lot of feedback from you guys, like you're going, whatever, okay. Is this feeling like it's just too convoluted to understand, or is that okay? There, there are other ways we could do it. Of course, in order to calculate the change in the kinetic energy, well, we know this is from the top of the water to the bottom of the water. We know the speed at the bottom of the water. We only need the speed at the top of the water, and we could have gotten that from a good old-fashioned kinematics calculation, right? But I would have had to do F net equals ma on a frictionless ramp, figure out what ax was, and then use one of my kinematics equations for constant ax with initial speed being 0, Vx initial is 0, and I want my Vx final. And then that would go into here. But I'm trying to short circuit that a little bit and do it in here. It's almost like one step to calculate this rather than separately calculating A and so on. But there's nothing wrong with doing it the other way. I'm slightly predisposed to doing energy methods right now because, things that involve work and kinetic energy and very shortly, potential energy as well. Okay, that took long enough. Any more questions on that one before we just very, very quickly discuss 5 conceptually? 5 says a 0.3 kilogram ball moving to the right in deep space encounters a frictionless U-shaped tube attached to a large asteroid. I just attach it to an asteroid so it doesn't get shot forward when the ball hits it. It essentially stays at rest, and the ball goes through it and gets shot out the other side. It just rolls right through it. Or maybe in this case it's frictionless, so it doesn't really roll, but it does get shot out the other side. It enters at 3 meters per second and it leaves the other side of the tube at 2.8 meters per second. How much work does the friction force from the tube do on the ball while changing its direction like this? How would you approach that? There's not too much calculation involved in this one, but where would you start? Yeah, so I'm going to use the work kinetic energy theorem. Initial is right before it enters. Final is right when it leaves. So let's just write down the whole thing. The net work done by all forces acting on the ball while it's going through the tube is equal to 1/2 mv final squared minus 1/2 mv initial squared. And I know all the information on this side, right? We're given the final speed, the initial speed, we're given the mass of the ball, so we're good on the right-hand side. We want not the net work, but rather just the work done by friction. So the question is, what other forces are acting on the ball as it goes through this U-shaped tube? It's no gravity. We're in deep space here. Yeah, I mean, there's essentially got to be a normal force from the surface, right? There's got to be a normal force from the surface, but it's doing zero work because like all normal forces, as something's moving along the surface, even if it's a curved surface, the normal force is always pointing at every instant perpendicular to the direction it's moving as it goes around all the way. And so it's doing little bits of zero work, zero work, zero work all the way around. So the normal force doesn't do any work. So the net force is only the work done by friction on the ball in between initial and final. So I have 1/2 times 0.3 times 2.8 squared minus 3 squared. It shouldn't be surprising that when you calculate the right-hand side, which is the answer to the problem here, you get something that's a negative number. Why should that not be surprising? Yes, because the speed decreased, so that's just saying you're looking at this side and saying, hey, I know this was bigger and that's smaller with the bigger number came with the minus sign. What about in terms of the works? How would I know that the work done by friction should be negative? Yes, Caitlin. Yeah, at every instant, just like the normal force is always perpendicular to the velocity, at every point, it's sort of scraping and pushing backwards against the direction it's going, and that's serving to do negative work. It's translating a little bit in that direction, and at that instant, friction's pushing back like this, so it's doing a little bit of negative work, a little bit of negative work, a little bit of negative work all the way around. Even though the direction's changing, it's doing a lot of little bits of negative work. So the answer there is minus 0.174 joules. Okay, any more questions on those? Those were just leftovers from last time because we spent so much time doing other stuff, but that's good. Work kinetic energy theorem. So now we're gonna increase our generality away from just looking at particles a little bit. And this is some of the most difficult material, at least understanding where it comes from. Again, my point in class is not to go through everything you saw in the videos. I'm going to do a high-level kind of summary of it. The details are all there in the videos, and to some degree in Giancali, although sometimes he's a little bit sketchy with the details. Oh, here was an example we did in the video. Someone drops a ball from from rest at the top of a skyscraper, and what's going to happen? Well, it starts accelerating a lot at first, but then it reaches close to what we would call the terminal velocity of that ball. Terminal velocity is when, well, gravity is always pulling on the ball with the same force. But as the ball goes faster and faster, the air resistance force gets bigger and bigger. The faster you go, the more it pushes back. And at some point, those two forces almost balance out, and that means it's going at just about constant velocity. So it starts falling with an almost constant speed. So I don't know if it's at terminal velocity here, but we're told when it's fallen 400 meters, it has a certain speed at that location. It's very close to the terminal speed. What's the network? How would I do that? Well, the network, whenever I see that, I think of, and I used to use a book that instead of using KE, it just used K. So sometimes you'll see K and U instead of KE and PE. Those are just from a different book. You might see different notations. So that's easy. I know the initial speed was 0, the final speed was 20, so I can calculate that. How much work is done by gravity? Well, I know gravity is a simple constant force, so I can use our old formula Fy times delta y to calculate the amount of work associated with it. C, how much work is done by, this means air drag or air friction, right? That air resistance force while it's falling. Well, I know it should be negative because it's more or less always pushing back against the direction that the displacement is going in. But I have no way of knowing how to calculate it directly because it's a complicated force. When something's not moving very fast, it hardly pushes at all on it. When it's moving really quick through it, it's a huge force. So it's certainly not a constant force. And your force has to be constant to use this formula. That's the only reason we could use it there. So our only choice is to go indirectly and use the work kinetic energy theorem. We know the net work, we already calculated in A, was 100 joules that's done. That's coming from, well, what forces are acting on it? The air drag force and the gravitational force. So we know the net work, we know the gravitation work done by gravity. We can back out the drag work that's done. Not surprisingly, it's a negative amount of work. There were a couple other just sort of short ones that I think are more conceptual than anything. This is sort of like our U-shaped tube. An astronaut twirling that rock on a string or whatever it is, a mass on a string in a circle. So it's in uniform circular motion. Deep space, no gravity or anything like that. How much work does the string do on the ball during a half of a revolution? And the answer is 0. Someone help me make an argument for that. There are several ways you could go to make that argument. I'm assuming it's not slowing down, it just keeps going at the same speed. Yeah, one way is just to think directly about what work means, and we know what positive, negative, and 0 works are. The tension force, you know, when it's rounding the top here, there is no top and bottom when you're in deep space, but at least the way we're looking at it. As it's rounding the top, it's moving or it's being displaced in that direction. The tension force is perpendicular to it, and it's always perpendicular to it. So it's a little bit of 0 work, a little bit of 0 work, a little bit of 0 work, all the way around for half revolution. It doesn't matter half. I just put half in there randomly. It would also be 0 for a quarter or a full revolution or 12 revolutions. It's just constantly doing little bits of 0 work as it steps around the motion. Anybody see a different way we could use the work kinetic energy theorem to conclude that it does 0 work? Yes. Its speed is constant. So if we say initial is when it starts the half revolution, final is when it completes it, the 1/2 mv squared doesn't change. So the difference in 1/2 mv squared will be 0. And that means the net work done by all forces on it has to be 0. And there's only one force that's doing that net work, right? There's only one force that contributes to the network. So the answer is 0. It's the same with moon orbiting Earth. If we imagine it's a perfectly circular orbit, you know, it's not exactly circular, but if we imagine it is, then the moon's speed isn't changing as it goes around Earth, and that means that the gravitational force from Earth is doing 0 work on it. It's always perpendicular to the direction it's going all the way around. Two different ways of seeing the same thing. That was problem 4 there, and then problem 5 was a car suddenly applying its brakes and coming to a stop in a certain distance. So it takes 50 meters to stop. We know the mass of the car. We know its initial speed. Its final speed is 0. Find the work done by the road on the car via friction during this process. Well, I know the initial speed. I know the final speed is 0. It sounds like I can calculate the change in the kinetic energy. So let's see where that gets us. That change in kinetic energy is equal to the net work done by all forces. And then you've got to ask yourself, well, what forces are reaching in from the outside of the car and really strongly affecting it? Air resistance probably pretty puny here. I don't know if I said ignore it, but I am ignoring air resistance in this process. The road is really pulling on the car, right? As the car slams on its brakes, it's going in this direction. It's trying to push the asphalt forward, and the asphalt is pushing back on it as it's going in this direction. So that's negative work that the road is doing on it as it goes in that direction. But there aren't any other substantial forces that are doing work. Of course, there's a normal force, but it's doing 0 work. There's a weight force, it's doing 0 work. So the net work is just due to the force from the road on the tires in this case. And of course, it's huge because it was going fast and it has a huge mass. Okay. We've still got a long road ahead in chapter 6, but let's just step through it at kind of a high level. Again, the work kinetic energy theorem relies on the fact that the thing that we're considering the work involved, that the forces are doing work on, is a particle. That means it's just a rigid body that only translates. It can move down and over and stuff like that, but it's not allowed to rotate. And it certainly can't have any squishy forces inside. In other words, it can't be like a floppy human being. It can't be like these two masses that are connected by a spring so that as time goes on, maybe it stretches out in the final state or something like that. That can't be our system. That's not to say we can't analyze this, but we would analyze it by thinking of this as one particle and this is another particle, and we could calculate the net work done on this one and the net work done on this one. So we're going to generalize to systems that have springy internal forces in them, like the two masses connected by the springs. And we're going to do it in the following manner. We can generalize this theorem. We were thinking of it as applying to just one object. But we could imagine, say, 3 objects in an initial state, and they all behave like particles in that in going to the final state, they just get translated around. They move in space. Maybe they change positions with each other and stuff like that. But they're all 3 behaving like particles during this process. And the work kinetic energy theorem applies to all 3 of them, and therefore it applies to this whole collection. So if I think of this collection of particles as being kind of a system, then I could say, well, the net work done by all forces, and that would include forces between these. Maybe these have an electrical repulsion between them, and other forces that are reaching in from the outside. We have to regard all forces equally here. That work done by all forces is equal to the change in kinetic energy, and the change in kinetic energy is just, the kinetic energy of this system is just going to be the sum of the individual kinetic energies of the pieces. So now we're going to generalize using that idea that the work kinetic energy theorem applies to systems of particles, collections of multiple particles as well, in sort of a trivial way, to regarding a system as something that could have a springy internal force. Like this is a very simple one. Something more complicated might be like a human body. We'll never get to something that complicated, but here's a simple system that's not a particle. My system is this, and yes, I got to make sure I'm sharing the slides there. My system is this one on the left-hand side. It's 2 masses connected by a spring, and in going from the initial to final state, both those masses translate through space. We're going to ignore their rotation. We'll treat them like point particles for now, so we're not going to worry too much about the individual mass rotations. But also the spring stretches. So that system, this thing, is not behaving like a particle, but still we want to develop some sort of relationship between work and energy going from the initial to final state. we're going to only want to include the work done by forces that are reaching in from the outside. This force, this spring force between two parts of the system, we're going to treat it as what we're going to call an internal force. In other words, it's a force between parts of our system. And since we're treating it as an internal force, we're going to want to ignore it when we calculate the work. And the motivation for that is this. If you have a container of gas, maybe a little gas, it's got a piston on it or something like that. And I don't know anything about all the intermolecular forces between all the particles in this gas. But I, as an external force, could, take a little piston or plunger on this side and actually compress the box of gas. And I could calculate how much work I'm doing, right? Because I might say, oh, I know what the force is, and I'm pushing it through a certain displacement like that. I know how much work that was done by an external force on the system. What I don't know is all the individual forces between the individual molecules. That would be something complicated. So we want a theory or a way of setting this up so that we only, when we have a complicated system, and this is a very simple example of a complicated system, we want to only refer to forces that are reaching in from the outside and the work done from them, not the forces between molecules. And you can think of this spring. Of course, molecules don't have springs in them, but molecules exert forces on each other. And you can think of those forces as being like an invisible spring that keeps them from running into each other and causes them to bounce off of each other. We want to be able to ignore those. So we're only going to calculate the net work done by external forces. That's what I'm calling W net by external forces. Or we want to relate that to a change in energy. And again, I'm just reminding you here that when we say, when we calculate the work done by a force, we consider the displacement of the location at which the force is applied. When we've got a loose, floppy system, different parts of the system are moving by different amounts. If there's a force on this piece of it, we have to concern ourselves with how far it's moving in calculating the force there. Okay, so the important difference with what we've already found out about the work kinetic energy theorem is that if a system's not rigid, it need not gain kinetic energy, even though the net work done by external forces on it is positive. If something's a particle and sorry, I keep switching back and forth to the camera so that I can record the parts of me gesturing or something like that. If I have a particle, here's a particle. If an external force does some net work on it, positive work, it has a positive increase in kinetic energy. It speeds up, right? Here's a complicated, or not so complicated, but it's more complicated than a particle system. My system is going to consist of these two masses, which keep coming unhooked from each other, but connected by a spring, just so we can visualize the force, although this might represent some invisible electric force or maybe gravitational force between two masses. Okay, so here's my system. My hands acting on this are going to be the external force. So let's imagine it's sitting there in outer space, happily floating. I, as an astronaut, come up to this system and I say, I'm going to start exerting a force on this, start it at rest, stretch it out, and then let it come to rest again. So we started at rest, we ended at rest. What's the change in kinetic energy of this system? And by kinetic energy, I just mean you add up all the kinetic energies of the individual bits of mass, which are these two pieces here. It's zero because the whole thing started at rest and the whole thing ended at rest. I'm an external force, or several external forces, right? I've got one external force for each hand. My right hand, which is over here on your left side, is it doing positive, negative, or zero work in this process? And why do you say that? Which way is my hand pushing on the mass? Towards the wall over there. Which way is the mass moving? In the same direction I'm applying the force. So this hand is doing positive work. What about the other hand? Positive work. So the net work done by only external forces in this case, I'm not talking about the spring because I'm going to treat it as internal. The net work done by only external forces is positive, and yet the change in kinetic energy is 0. So that means, well, we didn't expect it to apply to something that's not a particle, but that's just demonstrating why or how it's not going to work there. Okay. So we're going to patch it up a little bit. In this case, well, we already know how to treat systems like this. My whole problem with not being able to deal with this is, this was just an example of me pulling my hands outward. The net work done by external forces is greater than 0, but the change in kinetic energy is 0. Here is another example of that. Imagine I've got a system. My system is going to be a book or a mass. I didn't bring my book with me, so I'll take this mass right here. And Earth underneath it. The whole thing, this mass plus Earth, is going to be my system. And I'm going to consider that gravitational attraction between the two to be an internal force in my system. As I raise this book up, so my hand comes in. My hand is an external force. I come in with an external force and raise it up. I do some positive work on it with my external force, right? I'm pushing up and it's moving up. That's the hallmark of positive work. And yet, it doesn't change kinetic energy. The Earth's not moving any faster, and this isn't moving any faster. If I raise it from rest to another rest position here. So with more complicated systems, we're going to have to be, all of this, you know, depends on the fact of how I've defined my system, right? We're excluding certain forces and saying that they're internal forces, and so you got to be careful in how you define your system. And unfortunately, in this case, there are often going to be several ways we can solve the problem by choosing different systems. And some of them might be a little bit easier. So we want to get good at deciding what kinds of systems. Here's a third system I might take. This is the same situation. I'm going to raise a book with my hand. But my system, instead of being the book plus the Earth and treating that gravitational force between the two as an internal force, here I'm just going to say my system is just the book. Hey, that's a particle. I know how to deal with that. But let's just calculate the work that's done by it. Let's suppose I reach in with my hand, that's an external force, and raise the book. Well, my hand is now not the only external force. Since my system's just the book, the gravitational force from the Earth is also an external force. And they're going to do equal and opposite works. So as I bring it from rest down below to rest up above, those two forces, one will do positive work, one will do negative work. The net work will be 0. The change in kinetic energy was 0. And I'm not surprised by that because my system was a particle here. So we got to be very careful about defining our system. That's going to be absolutely key in understanding this. If your system's a particle, you can always use the work kinetic energy theorem. If it's not a particle, then we need to be careful and we're going to define something else. So we're going to start to develop a series of work energy relations. And here's the one we already know up at the top. If we have a rigid non-rotating object, a particle, or a collection of such objects, we said it sort of generalizes to that case, we have the work kinetic energy theorem. Now our system is a non-rigid, springy system, which are masses connecting by internal forces. And we're only going to concern ourselves with the net work done by external forces. And the question is, what goes on the right-hand side? And the answer is, well, we actually can use the work kinetic energy theorem to figure out how to solve this, because the whole confusion is coming because I'm calling some forces internal and some forces external. But if I treat them all as external, then the two parts that are connected by a force, I can just treat them as two separate particles. And in doing that, I'm going to skip a lot of the details here because, again, they were in the details of the video. But if I do that, instead of thinking of my system as two masses connected by a spring, I'm going to treat them as just two separate masses. And now the forces that are doing work are not just my left hand and my right hand pushing it apart, but also the spring force on the left mass and the spring force on the right mass over there. And to that kind of way of thinking about it, I can apply the work kinetic energy theorem, except that on the left-hand side, I'm going to separate it out into the work done by external forces only, plus the work done by internal forces. And here's the trick. Since we want only the net work by external forces to appear on the left-hand side, I'm just going to put this thing over on the other side with a minus sign. Okay? And hopefully we can calculate it. In this case, we just make a redefinition. The negative of the net work done by internal forces is called the change in potential energy of the system. There's a little bit of a subtlety that I'm passing over here for the sake of not being too confusing at once, but we're just going to redefine that to be the change in potential energy of the system. So our new law, we're going to have to figure out how to calculate potential energy, but if we can do that, we know it's related to a work, and we know something about work, so hopefully we can figure out how to calculate it. Our new law that applies to non-particle type systems is the net work done by only external forces reaching in and pulling on parts of the system is equal to the change in kinetic energy of the system. That means the change in all the 1/2 mv squareds of the parts that comprise the system, plus the change in potential energy of the system. And we're going to have to learn a little bit about that. So now we're going to cover a very small number of potential energies, and we'll practice with doing them on the next worksheet. Okay, so we've now got two different work energy relations. One simple one applies to just particles, but this applies to things that aren't particles. It can be a whole bunch of masses that are connected by forces. They might be real springs, or they might be gravitational forces that are like invisible springs, right? I can think of, it's almost like when I have this mass here and I raise it up, I can imagine there's a spring connecting it to Earth, and I'm stretching that spring, right? I have to do a lot of work to stretch the spring out, and then it wants to contract. If I let it go, it's going to contract and pull the mass down. That's a way of kind of visualizing that invisible gravitational force. So now we're on to this, and we're going to take these one force at a time and practice with them. How do we calculate the change in potential energy? If we had that, by definition, the change in potential energy is the negative of the net work by all internal forces. How are we going to do that for a gravitational force? So let's do that first. And I'm just going to tell you what the result of it was. There's a very straightforward calculation because I know how to calculate how much work is done by the gravitational force. Gravitational force is constant as something goes up away from Earth or down towards Earth. So if we're talking about Earth being, my system being, Earth is down there and some other simple mass is up here, and we're stretching that invisible spring or letting that spring contract. It's not really a spring, it's the gravitational force. We know how to calculate those works, and the upshot of it is that we can get an expression for the potential energy due to gravity on a massive object near Earth. So the object we're assuming that's near Earth has mass m. And we're always going to assume that plus y is in the direction upward from Earth. There's an assumption about that that goes into this. And then with the potential energy is mgy, where y is a y coordinate that increases as you go up from Earth. And let's see how to practice with that. Oh gosh, I have a lot of reading response questions, or at least big ones here. Maybe it's good to take a break from this discussion. Then we'll do some numerical examples with it. If potential energy refers to the energy stored in a system, do we have to change what we define as a system to then consider an object's kinetic energy? For example, when a book is held in the air, the hand, book, and Earth are all one system when describing the book's potential energy. They could be, or they might not be. I might take my system to just be the book, but that's something we could choose to do. And then there's going to be a potential energy associated with, it depends on what your system is, but there might be a potential energy associated with the gravitational force between the book and Earth. As soon as the hand lets go of the book and the book starts to fall towards Earth, so I take my force away, or my hand force away, and then we're just talking about the book being attracted to Earth. Do we suddenly change the system to just encompass the book? Well, effectively you would, because once I release my hand's not exerting a force on anything anyway. So if I had decided to put my hand into the system, it was not going to contribute after I let go of it anyways. So I guess in this case, my temptation would just be, I would tend to, in this case, if we've got a book near the Earth and my hand reaching in and exerting a force on it and then letting that force go, I would tend to take my system to be either book plus Earth, and the gravitational force is an internal force, and my hand is an external force, which suddenly disappears. Or I might just treat the book as a particle and treat gravity as an external force and my hand as an external force. And then the problem might look a little bit different, but we should get the same answers in the end. So part of the answer to this question is, well, you know, you'll sort of get this intuition as you do a lot of problems associated with this. It seems really confusing at the beginning. It seems as if there are different times in which a particle, especially a system of particles, is able to be labeled as being able to be defined by the work kinetic energy theorem, and sometimes when it is not. Yes, we just saw that with the book and the earth being the system with gravity and internal force, or just the book being my system. Is this something we would have to state, such as when we state our axes in kinematics and force problems? Yeah, that's a good way to think about it. You know, when we first started talking about kinematics, we said you always got to state your axes. You always have to state, or at least know in your head, what is your initial and what's your final, right? And this is the same kind of thing. In using energy methods to solve for, say, a final speed of something, because it's going to come out of that KE final, right? I could solve for V final, because it's hidden inside there. I have to carefully define what system I'm going to use, or I might confuse myself. I might, for part of the problem, think of the system as being the book plus the earth, and then later on, in my head, confuse it and think, oh, I'm just talking about the book later on. So you do have to be careful, and I would think about that carefully. We'll see examples of where we change our mind and do it two different ways. How can there be work involved with potential energy? In the previous sections, we gave an example of someone lifting up a grocery bag vertically and said that there was no work involved. This must be from the book, because I don't think I talked about a grocery bag. But that bag would have potential energy. So that's sort of true. And a lot of physics textbooks are a little bit sloppy about this. When I say, oh, look, here's a mass. I'm raising it upward. The mass has more potential energy right now. I raise it up away from the Earth. And we'll see from mgy, right? If plus y is up from that expression for the gravitational potential energy, when y gets bigger, you're increasing the potential energy. But that's sort of a sloppy way of saying it, because this thing I'm holding onto is a particle. And you might say, particles don't have any potential energy. They can only have kinetic energy, right? This thing might be moving, and then it would have kinetic energy. But there's no springs that could store potential energy in this. So when you say, I'm raising this up, and this has more potential energy, you should really be saying, I'm raising this mass up from Earth, and the system consisting of this mass plus the Earth, where gravity is an internal force, has more potential energy. And it's really cumbersome to say that, but you will confuse yourself, at least in the more complicated problems, if you don't. And I'm not sure about the brick example, but it sounds like the brick example, you know, you were thinking of the system, or Giancarlo was probably thinking of the system as just being the brick. It was a particle. And then in the other case with the grocery bag, the system was the bag plus Earth, with gravity being an internal force. And therefore, there was a change in potential energy that we had to take into account. Okay. Let's get into practicing with this. And I've got a bunch of practice problems just to work with this potential energy as mgy. We got to get used to using it. So let me pass out. I guess I'll ask any questions while I'm passing this out. I know that's a lot. That's probably the most difficult. This section we're in right now is the most difficult bunch of material in my experience in Physics 110 that we talk about. It's just seems very confusing, but you'll get used to the problem-solving aspect of it. And though maybe it won't seem second nature, it will seem a lot more familiar after several days of problem solving. So there's a lot of problems in here, and we're going to work through them all over the next couple of days. And just to get warmed up, let's do one together, just to see how to apply it. This is supposed to be a very, very simple application of this principle, but it all seems really confusing when we first encounter it. So I'm looking at problem 1 from the collection I emailed today, if you're zooming in. Oh, I'm sorry. How did I must have just gone diagonal and missed you guys. I thought I had a lot left over. Okay, so first problem on here says, use energy methods. Okay, this is a problem that we could have solved using kinematics. That's not going to be true of all problems we're doing here, but at least this one, if you, I mean, you can think about it, it's something we would have done a while ago with kinematics. So let's not use kinematics, rather we want to use our energy methods. And there may be more than one way to solve the problem by choosing different kinds of systems. I'm going to tend to use systems that use potential energy just because we just introduced it and I want to practice with using it. But we could also try solving a problem two different ways. Once treating a system as a particle and then a different system that has some internal springiness to it. A 0.5 kilogram ball is thrown straight up at 3 meters per second from Earth's surface. Find its speed after it has moved 0.25 meters upward. Everybody, and we're ignoring air resistance. That sounds like a typical free fall kind of problem that we did back in chapter 2 even, because it's a one-dimensional constant acceleration kinematics free fall kind of thing. All right. Let's use energy methods. So I've got to define my system, and I'm just going to make a decision for my system being really everything that's described in the problem. So I'm going to make my system springy. My system is going to be the ball that's going up plus Earth, and gravity is going to be an internal force between parts of that system, okay? And I'm going to write it down explicitly because we want to make sure we understand what our system is. Especially early on in the problems, you got to get used to naming it explicitly. So I'm just going to say ball plus Earth, parentheses, gravity is an internal force. Just to be clear, you know, because just because you have two parts to a system, I could have a force that's external. Like I could reach in with both my hands and say they're external and they're between parts of the system, but we're going to treat gravity as an internal force here. Okay, so my only choice is I can't use that first work energy relation, the work kinetic energy theorem. My only choice is to do the second one. And that says the net work done by only external forces, that means excluding gravity, right, is equal to the change in kinetic energy of the system. So the ball is going up. Of course, the ball is changing kinetic energy. I'm taking that you have the intuition that the Earth's not going to do much moving. So the Earth is actually going to have just about zero change in kinetic energy. Even though it's part of the system, if the Earth had a much smaller mass, then maybe it might do significant moving too, but it actually pretty much can be treated as at rest here. Okay, what external, if my system is this one up here, what are the external forces we're talking about? And air resistance is negligible. So what are the forces on the parts of my system that are moving? Because those are the only forces that can do work. We're looking for forces that are on my parts of my system that are moving, so that's the ball, that are actually doing work and are external. Well, it's none, because the only external force that sounds like as the ball's rising up is gravity. You know, air resistance we could treat as external, but we're told that it's so small it's not going to do any work anyways. So in this case, because I've essentially put everything that's of concern in my system, there aren't any forces left over to do work that are external. All the forces that are important here are internal forces, so no external forces do work. Okay, the only force that's slowing down or speeding up things as parts of the system are moving, and the only thing that's moving here is the ball, not Earth. The only thing that's doing work is gravity, and that's an internal force. Oh, I'm sorry, I'm still in, I need my delta PE. I didn't finish writing the equation. Okay, so let's write it down. Change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. Just putting in the stuff. Let's also put in the potential energy. Remember, the potential energy associated with gravity, and this is actually only true for when you have an object gravitationally attracted to Earth and it's near Earth. So this is true at near Earth's surface. Okay, then the correct formula is mgy, where plus y is up. Okay, so let's write that down. That's, plus mgy final minus mgy initial. That wasn't so bad. Now I just need to think about what I can plug in there, or what simplification. Anybody see a simplification I can make right away? What could I do to both sides of that equation to make it a little bit simpler right now? Yeah, I've got a common factor of m in everything here, so I could factor out an m and then divide both sides by m. M's not 0, so 0 divided by m is still 0. The left-hand side would stay 0. And the right-hand side, the m's would just disappear. So I'm just going to imagine I've divided everything by m, and those m's have disappeared. The left-hand side was divided by m too, but 0 divided by m is still 0. Okay, now I've got to plug in. What's v final in this problem? That's what we're looking for. So this is going to be our variable. Maybe I don't know what to do. I'll underline it. That's what we're going to hope to solve for. What's v initial? 3, is that what it was? Okay, we'll plug in a 3 there. What do I know about y final and y initial? Yeah, or we really know, we don't know about y final and y initial individually, but I know that y final minus y initial is 3.25 meters. So another way to say, well, now I've got gy final minus gy initial. I could write that as g times y final minus y initial, and that's just delta y, right? That is our 0.25 meters. Okay, so I can plug that stuff in and solve for v final. And I get v final is 2.02 meters per second. We could have done the same thing with kinematics. Just because this, before we go and do some of these other problems here, I want you to do the next one next, which is very similar to this, so you can practice doing it yourself. But just to mix it up a little bit, let's suppose I decide I don't like this system. I'm going to change my system to just be the ball that's doing the rising. But I'm still not going to do kinematics. I'm going to try to use energy methods. And I go to my collection of energy methods that we've done so far, and I say, well, my ball is a particle. So the work kinetic energy theorem applies to it. So I could solve it that way too. So I'll do that in red here. In this case, the relevant relationship to use is the net work done by all, that's what net means, all forces, not just external or internal, they're all external if you're talking about a particle, is equal to just the change in kinetic energy of the ball. And so in this case, what goes on this side? How much work is done by forces here? Yeah, gravity does work. Okay, well, I've got to think about calculating that work, but luckily it's a constant force. It moved upward by 1/4 of a meter, and the gravitational force was mg, and in this case, it's a 1/2 kilogram ball. So the work done by gravity, is it positive or negative? What do you think? Negative, because gravity's pulling down and it's rising upwards from initial to final, right? So it's negative. The gravitational force is, what did I say, 0.3 kilograms? Is that the mass of it? I don't know where I got that from. 0.5 kilograms. Okay, so the gravitational force is that times 9.8. And then times distance, 0.25. Okay, that's the left-hand side. Gravity is the only force that's doing work on it as it's moving upwards. Any questions on this calculation? This is what we were doing yesterday, right? It's our Fy delta y kind of thing, right? And in this case, delta y was positive, but Fy was negative, if you like. And that's equal to 1/2 mv final squared minus 1/2 mv initial squared. And let's just compare these two sides, right? I could, in this equation, cancel out the m's here, because I've got an m factor on the left-hand side and the right-hand side. After I've done that, I've got a minus 9.8 times 0.25. What do we have right here? A plus 9.8 times 0.25, right? If I brought it over to the left-hand side, it would become a minus 9.8 times 0.25. So we're really doing the same thing. It feels a little bit different, but we're getting the same equation when we choose a different system. And in this case, I'm going to get exactly the same final speed when I solve for it and plug in the other stuff there. So it doesn't matter which system you use, although we'll see in some cases we will know how to do it one way even though we don't know how to calculate the work. So sometimes if you have a non-constant force, here we got lucky because gravity's constant. We could use our old friend Fy delta y. But if you have a non-constant force, you may not know how to do that. But here there are choices. All right, try problem 2. Is that what I said? I guess I didn't say it on here. Why don't you do problem 2, and then we'll do exercise 3 together. Problem 2 is almost the same kind of thing. It's just got a different final state. We can take a break, yeah. I mean, take a break right now. Other people, if you don't want to take a break, by all means, keep going. I'm going to take a break and sit down here. I told you, chapter 6 is pretty intense, but part of feeling okay with it is just practicing that problem solving and feeling like if you've seen it in 8 different contexts, you start to sort of put the pieces together. And we've only seen it in like 1 context so far, so it's still confusing now. Yeah, I mean, I will log in just so I don't have to log you out and me back in afterwards. It just takes too long usually. So I'll bring my stuff up so it's sitting in the background, and you can just put yours on top of it and display it over there. What are you going to use for your slides or whatever? PowerPoint, yeah. Huh? Oh, okay. Google Slides, I suppose it's called, yeah. There was a time when something called Prezi was more popular. Do you know Prezi, where like everything spins around and it zooms in and all that kind of stuff? What's a nightmare? Formatting, yeah.
Do we need to run our topics by you, or?
If you're worried about it, you're welcome to. You know, most people have pretty good sense of, you know, as long as it's connected to science or physics, even better, and some ethical or personal concerns or interest. And that could be anything that's important to you or a concern of society as a whole. You know, so people have done environmental things. Sometimes people do things associated with their majors. Like I've had philosophers talk about some philosophical concept that was related to physics or what we were talking about in class, but it was a personal concern to them because they were really invested in it, and that's fine too. Yeah, it's going to be good to get back to regular old semesters. I think all the faculty is getting tired of, I'm not used to talking for this long. I'd spend most of the day not talking to people. So like talking so much is kind of tiring. It's sounding like I heard a rumor from someone who talked to someone in the administration and said it's seeming very unlikely. I think there's been almost all negative feedback or downsides to it and very few upsides to it. And if we thought there were a huge probability that things might really turn south in spring and get really bad, that might be a reason to go for it. But now that we've made it through several weeks of fall and it seems like no disasters are happening. A lot of big universities, when the students came back, like 2 weeks later, they were like shutting down. Since that hasn't happened at Center, it seems like we're only going to get better at managing it, one would hope. And, optimistically, if Fauci is right, we'd start to have a vaccine by end of year. So we might get it on campus optimistically mid-semester in spring. And so that helps bring up your optimism about what might happen. And then I can stop recording Zoom sessions and have everybody in class. That'll be nice.
I wonder how drastically Zoom stock is going to plummet after the pandemic starts.
I don't know. I think some of it will stay on, because companies now have realized that, hey, people can get a lot of stuff done remotely, and there's no reason to travel a lot of times if you can have a remote meeting and you're already good at doing it now if you're used to it. So my wife is at home, but she works in Frankfurt, and so she usually commutes. But she said, we've actually become more efficient because people don't sit around and just yak like they do at work. People will, talk about whatever. And when they're at home, they only call each other with a Zoom call when they actually have some work to do. So it's kind of lonelier. That's the downside, but. All right, so when you're mentally rested, try problem 2 on there, which is, it's really just mimicking kind of what we did there. So I get 0.459 meters. And looks like most of you are still working, and that's because you're probably doing it from scratch, but with very little adjustment of what I've done in blue, say on the board, we're just gonna change what initial and final mean. So I'm gonna stick to the blue convention here. My system is the ball plus earth, and gravity is gonna be an internal force. So I'm gonna use this same work energy relation. And again, there are no other external forces of substance acting on any of the moving parts of the system, so the net work done by external forces is still 0. The only difference is my initial is still going to be just after release, but final now is going to be defined when it momentarily comes to rest at the highest position. So my V final is now not what I want to solve for, but rather it's 0. Right? Final speed is 0, so 1/2 mv final squared is 0. Initial is still 3 because I just used the exact same problem. And now we don't know what y final minus y initial is. That's what we want to find, how far it goes up. So to be even more compact, I might call y final minus y initial delta y. And delta y is our variable that we want to solve for. Right? So that would mean, well, this is 0. I do 1/2 times 3 squared, put that over there with a plus sign, and divide by little g, and that seems like that would give me the answer. If you don't like doing several things in your head, it's a good idea to do one algebraic step at a time. Or similarly, if I went with the red convention, the 0.25 would now be my unknown. I would say gravity does some negative work, but I don't know how far it goes up vertically. But there's some amount of negative work associated with a force being applied as it arises, and it's there. And now the final would be 0. And it's exactly just a rearranged version of that equation down there. So in this case, I get delta y is 0.459 meters. So you're seeing some examples of things that we could have done with kinematics. Maybe they're slightly simpler here, maybe not, though. I'd say it's about the same, because we already knew what A is. We don't have to calculate A in this case, right? And if you did the kinematics calculation and wrote it down, you know, well, let's just talk about that. And you'll see it's actually the same thing we've got here again. It's just we're thinking of it a different way. What if I wanted to solve this second problem 2, using kinematics, what kinematics equation would I use if I choose plus y is up, say? The third one, the one with the squares, right? So it would look like this. V final squared, again, this is y components, is equal to Vy initial, I guess we call that 0 in this class, squared, plus 2 times Ay times delta y. Do you see any similarities between this equation and this one? Well, yes. I had a 1/2 here, but if I multiply everything by 2, the 1/2 goes away, and I get a 2 over there, and I've got a g, and I've got a delta y. That's like my 2 times g times delta y. They're rearranged and put in different places, but we're getting the same thing that we would have gotten before. So here it's about the same amount of work that we would have done if we did it with kinematics, but we'll find that we do have substantial savings, or there are some problems we can't do with kinematics later on. Any more questions on this one? I think we sort of done it 3 different ways. That's enough. Let's try problem 3 together. So this is, again, bumping up the difficulty a little bit, and we're going to look at something on an inclined plane. Energy methods. This is a type of problem we could have used kinematics on, but we're not going to here. So we've got a box on an inclined plane, frictionless, and we're given its mass. It's 2 kilograms. 40-degree inclined plane. And it's given a push up the plane. V initial, the initial speed is 0.75 meters per second. And later on, oh, am I reading the next problem? Maybe I'm reading 4. Yeah, I'm reading 4. Okay. Well, I'll do 4, and you can do 3, because again, they're almost the same. How about that? So I'm looking at 4, mass is 2 kilograms, initial speed 0.75, up the plane. Find how far it travels up the plane before momentarily coming to rest. Hey, that sounds almost the same. We just need to be a little bit more careful in this case. So the idea is later on, it's up here, it's about to start going back down the plane, and V final is 0. Okay, and I'm going to try to use one of my work energy relations. In this case, again, we could choose just the box that's doing the sliding and use the work kinetic energy theorem, but instead, I'm going to choose a more complicated system so we can practice with potential energy, and the only potential energy we know is gravitational, so the only force I'm going to put in it is the gravitational force between the box and the Earth. So here's a description of my system. It's going to be the box and Earth. Gravity is an internal force. But I'm going to imagine that this inclined plane is something that comes in from the outside and it's pushing on the box. It's an external force. It's frictionless, so the only we would normally call that force from the plane on the box the normal force. Normal force is external. You'll see how that makes some sense in just a second, but let's try to write down that second work energy relation. First, just write it. W net by external forces only is equal to delta KE plus delta PE. And that delta PE is associated with our internal force. So we're going to use that mgy formula for potential energy. Okay. Again, in this case, what? So there are some external forces here. Unlike before, this box is moving and the plane is pushing on it. The plane is like my hand coming in from outside. It's pushing on it as it's going up there, keeping it. So the plane is doing some work on it. How much work is the plane doing on it? Because that's our only external force, which is pushing on a moving part of our system as it goes from initial to final. How much work is the plane doing on it, or the normal force, as it slides up the plane? All right, there's our normal force pictured. Here's the displacement pictured. Would it be positive or negative? What was it? It's 0, yeah. The normal force does 0 work because it's always perpendicular to the direction it's being displaced, right? So much stuff I know is adding up all at the beginning of this chapter, but the normal force is the only external force that's acting on a part of the system. There's a gravitational force, but that's part of our big system that includes Earth. So the only force I need is the force from the plane, and it's frictionless, so its only force is the normal force, and it does 0 work anyway. Even though there is an external force, it's doing 0 work. Okay, that's equal to, okay, now I can go into brainless mode. 1/2 mv final squared minus 1/2 mv initial squared. And then the change in potential energy, again, I could write as mgy final minus mgy initial. And I could, just like we did before, we could factor out the mg. That's mg times y final minus y initial. That's the change in the gravitational potential energy. Gravitational potential energy is mgy, where we have to choose plus y is up. Okay, and I'm interested in how far it goes up the plane. Yes, how far it travels up the plane. And I'm not sure how clearly I said it there, but I mean as measured along the plane. Because when you say up, sometimes people think straight up. So let's just call that unknown distance delta x. You know, maybe delta x is that distance there. The front of the box moves as it goes up the plane. Is that delta x what goes right here? No, it's not, because plus y is always straight up. And as this thing goes up 4 meters at an angle, it doesn't go quite that far straight up. We need to figure out how far it goes up. When it moves that 4 meters up, this distance is what I would call delta y right here. Or y final minus y initial. And we can get that from a little right triangle, not surprisingly. This angle is also 40 degrees, so it would be delta x times the sine of 40 equals delta y. Okay? So this is my delta y. I could replace this with delta x times the sine of 40 degrees. And that delta x, I don't know why I'm writing it that way. It's 4 meters in this problem, isn't that right? Or am I misremembering? Oh, no, it is a delta x. I'm thinking of some other problem. I don't know where I got that from. Delta x is what we want to find out. Yes. How far it moves up the plane before coming to rest. Okay, what else do we know here? What's v final? Well, so I gave the thing that we want to find out. This is what we want to find out. How far it moves up the plane before coming to rest. So I gave it a name, delta x. Now, when we say the gravitational potential energy associated with a system that consists of a mass m and Earth down below where gravity is an internal force is equal to mgy. And that means the change in gravitational potential energy is going to be mg times y final minus y initial, right? Delta always means the change, which is final minus initial. This is how far it's gone up from the surface of the Earth, which is different than what delta x means. So I'm going to try to get a relationship between those two. Delta x is what I want. Delta y is what I need to substitute in here. So I'm going to express delta y in terms of delta x. And here's a little right triangle that's going to allow me to do that. Delta x times the sine of 40 degrees is delta y. Delta x times the sine of 40 degrees is delta y. Because another way to do it is I could have solved for delta y first, and then you could have used a little right triangle to figure out how to turn that into a delta x. That's another option. The important thing is they're not the same quantity. Is that enough on that, Sam? Okay. Please stop me with other questions too, because I know this is all confusing, especially the first few times you do these problems. What about v final? Do we know that? What about? Yeah, it's 0 because it's coming to rest. So I'm going to choose, it's my choice, but I'm going to choose because I know what I want for the answer to this problem. Final is just barely comes to rest. Initial is right after the push. So I know v initial. I think I know m, but I don't really need to know m because there's a common factor of m everywhere on the right-hand side, and if I divide both sides by m, that m would just disappear. But I think we were given m in this problem anyways. So it looks like I know everything except delta x in here, and I could solve for delta x. And I get, and not a very big number, must not have been a big speed, 0.75 meters per second. I get 0.0446 meters. So that's about 4.5 centimeters it goes up. It wasn't a big enough push. I just made up the numbers, and they seemed reasonable, but it doesn't go very far up this plane. It's a pretty steep plane. 0.0446 meters, or about 4.5 centimeters. All right, any other questions on that one? That was problem 4. Now you're going to back up and do problem 3. Well, how did you get negative here? It wouldn't really, because delta y I'm expecting to be positive, and I used a right triangle, so it seems like I would get a positive delta x there too. So v final is 0, right? This thing has a minus sign over here, right? So this is a negative number. And when we put it over there, it becomes positive. And then I undo the other stuff and get a positive number. Good question. That's always something to be aware of. If your sign doesn't make sense, you probably just, made a little error in your algebra somewhere. So try problem 3. Okay, I've tried to draw what is the change in the diagram up here. Here we're giving it an initial push down the plane, and we want to know after it's moved 1.5 meters down the plane, it should have a larger speed, presumably. It's speeding up as it goes down. What is that final speed? And I'm going to take, just for example, the same. If we want to do it more complicated, probably we could use just the work kinetic energy theorem with our system being just the block, but I'm going to stick with this system that we have here. So my system is block plus Earth, and the plane is someone who comes in from the outside and pushes on it in a frictionless manner. So starting with the same thing right here, let's just erase this because it's kind of a mess. But still, the only external force which is pushing on it is that normal force, and it's doing 0 work. So the left-hand side of net work by external forces only is 0. And that's equal to 1/2 mv final squared. There's the thing we want. Minus 1/2 mv initial squared plus mg y final minus y initial. I'm just going to factor out the mg again because that delta y is going to be of interest to us. Now the 1.5 meters isn't delta y. Remember, plus y is always up. When we're using that expression, mgy plus y is up. And so the question is, it looks like its y is going down. That's a negative delta y that we're going to have to put over there. And what is the magnitude of delta y? Well, it is how far it goes down. So the magnitude of it is the length of this side of the right triangle. But it's going to be negative, right? Because plus y is up, so delta y is negative. So how do I express it in terms of the 1.5? 1.5 times the sine of 40 degrees with a minus sign in front of it. So it's a negative delta y, 1.5 times the sine of 40 degrees. And now this is my thing I want to solve for. The initial is 0.75. And I think I know everything. And there you could cancel the m again and just solve for what v final is. I'm getting 4.41 meters per second. Yes, Sam?
So then if your delta y is negative, delta g is negative.
Little g is never negative. Little g is always positive 9.8. If you choose plus y is up, then and you're in free fall, right, or projectile motion, then ay would be minus little g, or minus 9.8. If plus y is up, then ay would be minus 9.8 when I'm throwing something through the air, right? So components will be negative, but little g is always defined to be a positive number. If you want it to be negative, you got to put a minus sign in front of it. So when we write a formula, like when this little g appears here, that means positive. The minus sign might come into the y, right? Because we said plus y is up, and maybe, you know, something goes downward as it goes from initial to final. But the little g is always defined to be positive 9.8 for us here in Danville, Kentucky. Anything else? Okay, I'm feeling like everybody's pretty tired, so I'm probably just going to stop there. Well, so let me just tell you where we're going, and then I'll answer Jeremy's question. Where we're going is we're only going to introduce 2 more formulae for the for potential energies. Whoa, how did I get way back here? I don't know. Oh, I know why, because I'm in slideshow mode. There we go. 2 more formulae. So we're going to define a potential energy due to an internal spring force. That's elastic force that several people asked about in their reading response posts between 2 masses. And then also, our gravitational potential energy is really rather limited. It's only valid for an object near the surface of the Earth, where your system is that object plus the Earth, where gravity is internal. I'd like to be able to move that object really far from Earth. But this expression mgy was defined or derived assuming that the object stayed close to Earth. So we're going to get a more general expression that looks a lot like the gm1m2 over r squared. That's valid for the gravitational potential energy between Moon and Earth, other planets, or an astronaut who's really far from Earth. Okay, and then we'll have 3 expressions for potential energy, and we'll be able to do lots of problem solving. All right, thanks for your patience. Don't get discouraged by, you know, what seems like a lot of confusing stuff. We're going to practice with a lot of problems. You see, there's a lot more to go in this worksheet here, and we'll be working our way through that tomorrow. 4.41 meters per second is the answer I got to 3. You're welcome. See you tomorrow. Are you going to stay and ask questions, or do you have to go?
Well, I didn't get to eat lunch, so I was gonna go do that and then go to practice. But could we meet before class tomorrow?
Yes, I don't have any meetings scheduled before class. So let's say, what? How about 12:15? Would that be good?
That's perfect.
Okay. So and tomorrow we're in the other room, right? The usual Thursday room.
Thank you.
You're welcome.
Are you available Friday? Because you beat me to it, because I was going to ask you about my test before.
Well, I mean, we certainly can do it now.
Oh, I haven't had a chance to.
You haven't had lunch? To what?
To like go over the answers.
Oh, okay.
I had a cell biology test this morning. I recommended my attention yesterday.
Yeah, let's think about it. You're welcome. See you tomorrow. Tomorrow, yeah, I probably couldn't do it any earlier than the 12:15 time.
Is she going over stuff with her test? Because I'm fine not.
She is not going over stuff with her test, but rather some older stuff that was on the test, and I think also some chapter 5 questions.
I mean, the questions I have, I'm fine with it not being private. Is that okay to come as well?
Yeah.
Okay. I'm going to occupy this space for a bit and do homework.
Okay. Carson, are you working on homework too?
Yeah, I'm just finishing it up. Practice. I'm just gonna get straight there. So I'm just gonna finish this here.
Sounds like a
Questions because like I know how to do them. Like first of all, for number 6 on the one that's due tonight, like I know how to do it, but it doesn't give you the math. So I think I have to wait for the math. I'm just like not sure.
Yeah, so 6, there are 2 ways to do it. One easy way and one hard way. The easy way is we're given a period and a radius of an orbit. You need something, Phil?
Do you know our balances that they measure larger masses?
Yes, I do. If you know where the air tracks are on the wall, I think it's the leftmost set of drawers, but it's one of the drawers on the left of that big wide collection of cabinets at the very bottom. In my lab, at the bottom left when you're looking at the air tracks.
Another one doesn't measure.
Yeah. I'm sorry about that.
I understand that it's like exactly the same as the problem that we did in the worksheet.
Well, and so the one we did on the worksheet, I think we used Kepler's third law, probably. And so Kepler's third law you can get from Newton's second law and gm1 m2 over r squared, but it just takes a lot more work. Kepler's third law makes this problem really easy. So Kepler's third law says that, at least if you remember, it had to do with that semi-major axis length in the period, but this is a circular orbit, so we're just going to call the semi-major axis length the radius. It said that for any object orbiting a common mass at the center, like the sun, the cube of the orbital radius divided by the square of the period is equal to a constant that's the same for every planet or satellite that's orbiting that mass. This constant depends on what the mass is that you're orbiting, but and it depends on capital G. So that means if we have, in this problem, what? An asteroid and Earth are the two things orbiting the sun, right? Oh, am I not doing the right one? I'm doing asteroid in orbit. Oh, okay. Sorry. I was looking at part 2, not part 1. So did you say problem 6? Coin on a turntable? Okay. Coin is placed. Yeah, this would have nothing to do with Kepler's third law for sure. That was going to be a really creative solution there. Okay, a coin is placed 35 centimeters from the center of a horizontal turntable. Turntable begins to rotate. When the speed of the coin is so big, the coin just begins to slip. What is the coefficient of static friction between the coin and the turntable? Yeah, so here's our coin, and we're not given the mass. That's what you said, right? I'm just going to put a little m in there, right, just as a placeholder, but hopefully it doesn't come into the solution. Let's see. And it's going around in a circle. We're given the radius of the circle. I don't remember what it is. For your version's different than mine. But if I did a free body diagram for this mass at this location, we would have a normal force. We would have a weight force. And, well, it's moving in a circle that looks like this. So there's got to be a force. Neither of those forces points at all towards the center of the circle. So there's still got to be a third force that's resulting in the centripetal acceleration, the acceleration towards the center. And that's coming from static friction. So static friction is always pushing directly inward. You know, it's sort of like if you're on a merry-go-round and you stand, you feel like you're being thrown to the outside. So friction's got to push you in. Yes. I mean, I would say first let's do an axis. And you are interested in the x one, I think is what you're saying, right? So if we do sum of the force x components equals max, this is the only one with an x component. I've chosen my plus x inward, so this one is actually not negative, but positive. Positive, let's see. And if it's just about to slip, but it hasn't slipped yet, that would be the maximum static friction force, which has the formula mu static times the normal force. And the normal force, in this case, has to be equal to mg in magnitude because it's not accelerating along the y direction, and therefore those only two vertical forces have to balance out. So I'm just going to substitute right in, if you don't mind this shortcut, mg for the normal force. So that's an extra kind of mental step we're doing. And that's equal to m, and the component of the acceleration towards the center is v squared over r. And now I breathe a sigh of relief because that m cancels out. And they give stuff in non-SI units. I mean, I would tend to just convert it to SI. It probably works out if you leave it in centimeters, but we'd have to check and keep all the units in. Yeah, I think it would. If we put everything in centimeters, all the centimeters cancel out, so you don't necessarily have to convert there.